perhaps why is particle size important to these kinds of samples. I did a study a few years ago of organic pigments using the LA950 laser diffraction analyzer. I'll show you that data. Some data we've collected through the years for inorganic pigments, something about inks. Then we'll focus in on a specific pigment, titanium dioxide, which I suppose is the most broadly used pigment in the world. We'll show data for titanium dioxide from both laser diffraction and dynamic light scattering, where we'll look at particle size and zeta potential. And then we'll wrap up with our conclusions for today. So let's define what pigments are. The pigments we're most interested in are materials that change the color of something. So pigments are there specifically so that our perception of a surface becomes a certain hue, color, tint, opacity, brightness, etc. So one way that pigments can change the colors that we see is that there's some kind of absorption reflection going on as light interacts with a surface that has a pigment on it. So in the simple cartoon above, we have red, green, blue. We have broad spectrum light hitting a surface with a pigment. But specifically, more of the blue light reflects than the other wavelengths, and therefore, to the observer, this appears to be blue. Down below, we could show perhaps a little more in terms of looking at, if we look at sunlight, which is a broad band across many wavelengths, as it interacts with a blue pigment. Here at the surface, it would be absorption and then also reflection at certain wavelengths. And since we have absorption here and reflection here, this would create a blue appearance to the observer. So this is what pigments do. And many times, pigments are particles. And the size of the particle has a big impact on the color, brightness, hues, opacity, tint, etc. of the surface coated that we are looking at. So I'll show here some of the physical perceived properties and also how the material processes depending on the particle size distribution of the pigments. These are specifically pigments made of particles for today's presentation. And they will change the hue and tint strength. Are they transparent or do they hide a surface underneath? How glossy is it? Is it glossy or is it flat? But then we also have to think about the processing of the material because these are powders, particles, like other particles in a chemical plant. And perhaps as you change the size and the zeta potential, they'll flocculate or aggregate at different degrees. If you reduce the particle size of particles in the suspension, you increase the viscosity. And perhaps that is important if you're looking at making paints. The same issue with particle size and zeta potential, and this is very important, stability, the shelf life of the pigment in the paint could have a big impact on that, and we'll look at the effect of the distribution of particles and how that might affect stability, and even weather resistance will be affected by the pigment particles. I was actually visiting a paint company who's a customer in Slovenia, and they were actually showing they have this house inside this building where they paint it and then hit it with wind and hit it with rain, and then they show the effect of different paints and how this will affect the weather resistance. The little chart over here is just a simple chart of showing this is gloss strength versus particle size expressed as a % greater than 1 micron. So perhaps this would be one of the values we'd look at if we were using laser diffraction, because we know as we change this % over 1 micron, the gloss changes significantly. So just a quick review of some of the physical properties that are dependent on the particle size and perhaps also the zeta potential. Since they're very small particles, that will affect the stability of a suspension. We'll start today when we start looking at case studies and applications with organic pigments, which are typically in the powder form. And we have lots of customers who just use like an LA950 or maybe even an LA300. I guess in this case for dry monitoring, it's always the LA950. But if you're doing dry milling and you want to measure it as a dry powder, you can just take the sample as you're milling it, bring it over to the instrument, perform a quick measurement, and find out when you've reached the endpoint of the desired particle size distribution as you do milling. If we're looking at powders that are dispersed in a liquid media, then we might be doing size, perhaps also zeta potential, although currently that might be a little more in research. But if we're looking at particles dispersed in a pigment, then perhaps we're doing wet measurements, and then we'll show you data from the LA950, both measuring powders as dry powders and dispersed in liquids. So for organic pigments, there are lots of people using laser diffraction for these measurements. This is a study I did a few years ago where I should again thank the company Lasco Colors down in Warwick, Rhode Island, who I went down to visit one day, and they were kind enough to give me these 4 organic pigments just to have fun with, and I gave them the data afterwards, something we're always willing to do with customers who let us use the data. And I just took these 4 organic pigments. We measured them as a dry powder in the LA950, the instrument you see here, where the powder just feeds through the dry powder feeder through the system. We look at the light scattering. We calculate particle size. We're not going to cover that today. There are plenty of recorded webinars on the website talking about the technology. Today we're just going to talk about using this technique and what the data looks like. But I note down here how we made these measurements. We used the small high dispersion nozzle. We set up the instruments so that the automatic feedback loop continually kept a continuous mass flow rate of particles through the system by measuring the concentration of particles and changing the vibration rate as it looked at the concentration. A great unique feature of the dry powder feeder in the LA950. We kept the air pressure down fairly low for these samples. They were easy to disperse. And then we just loaded up enough, did 3 consecutive measurements, and then looked at the repeatability. Because when you use laser diffraction, that's the first thing you test to say, should I believe these results? Do I have confidence in them? Is we look at the reproducibility of results, or repeatability. With powders, it's always reproducibility. And that gives us some indication of what do we think of the data we generated. So now I'll show you some of these results. This is for this yellow pigment. What you see for each of these samples, we ran them 3 times. This is showing the median value of the 3 runs. We calculate the mean of the 3 runs and the coefficient of variation, which is just the standard deviation divided by the mean times 100. And what you'll see here is for this sample, we got the coefficient of variation down to about 1%. You see over here some tails. This could be sampling as much as anything else. Laser diffraction is inherently a very reproducible technique. For the next sample we ran, which was also a yellow, but a larger particle size, we actually see that we had better reproducibility, counterintuitive to what you would expect, but a coefficient of variation down at 0.4%. Excellent reproducibility for the sample. This is 3 runs overlaid. Then we ran another sample of a yellow pigment. Again, the coefficient of variation down under 1%, close to 0.2%. And then a blue sample at about 25 microns, median particle size, and a coefficient of variation under 1%. So what you see here is just saying, these are really easy samples. You load them on the tray of the dry powder feeder, set up to run automatically, take 3 measurements. It'll be incredibly reproducible. You can have a lot of confidence in these results. Very easy to set this up to run automatically. The operator just walks up to it, loads the sample, hits a button, and you can easily generate data like this for your organic powder pigments. We'll switch from organic pigments over to inorganic pigments because now I want to talk about taking powders and dispersing them in liquid. In terms of method development, this is a little more involved because we need to disperse the powder and then perhaps see if we need to use ultrasound to disperse it to primary particles. What we see here is this tail of large particles. This might indicate there's aggregates here. It could be that we'd want to spend a little more time on method development. To be honest, I ran these samples 4 years ago. I don't remember exactly how we did it. But this is a red iron oxide pigment. I think I ran for a study for samples used in the cosmetics industry. And what we're showing here is dispersed down to, what's the median size? That looks like it's down in range of maybe 400 nanometers or so, 500 nanometers. Laser diffraction is an incredibly flexible tool. It can measure up to millimeters down to the nanometer scale. But a fairly easy measurement of an inorganic red oxide. Getting to a more controlled distribution here, this is chromium oxide green. And here I see that we noted we used a surfactant to wet the powder before we do the measurement. And then instead of dispersing it in DI water, we use sodium pyrophosphate. We have webinars on the website for method development where we'll talk about sampling and dispersion. We won't go into that today. But these are the kinds of things you need to do when working with taking a powder and dispersing it in liquid. We might need to do some method development looking at the proper concentration, in this case micro 90. And maybe instead of just dispersing in DI water, maybe we use some other add agent to change the ionic surface chemistry in the instrument while we're doing the measurement. And we see here a median down at 1.5 microns. Easy, easy stuff. We did a measurement of some aluminum oxide used as a pigment. And what you see here is a first peak down here at probably 300-400 nanometers. The median size here, it says right here, is 300 nanometers. But then maybe some aggregates, but we also just see this tail here. And so we took this sample, put it under a microscope, and it turned out that is just a large particle. So it might not be the case where it's aggregated. Sometimes there are just large particles. But really, to understand with laser diffraction won't really tell you are these large particles or are these aggregates. That's usually when a microscope in your lab comes in very handy, or an image analyzer like the PSA 300, where the image can actually give you a feel, aggregates versus just a few large particles. So we see here we used a different surfactant. AGPAL 630 is a non-ionic surfactant we use for a lot of samples like this. We use ultrasound for 15 minutes. That's telling me this was an external ultrasonic probe. So again, these details are telling us there was method development required to get these results. But if you'd like to hear more about method development, visit the website. We have various webinars devoted to that topic. In inks, there are pigments that actually are typically smaller than the other pigments we've seen so far. This was a pigment we just had from a inkjet hanging around the office somewhere, and we did measurements on the LA 950. You see a median size here down at 105 nanometers. Now, not every laser diffraction analyzer is completely comfortable measuring it at 100 nanometers and below. So this is kind of showing off one of the capabilities of the LA 950. It actually would be very comfortable measuring down to the 30 nanometer scale. But look at the repeatability here. This would be a coefficient of variation of like 0. So this is showing off how inherently repeatable laser diffraction is. This is taking a sample and recirculating it in the instrument, doing multiple measurements, and you'll see we get incredibly repeatable results, even for the sample that's fairly small. Actually, sometimes smaller particles, once they're dispersed, are the most repeatable results you can see. But the LA 950, very, very comfortable working down here in the nanometer scale. So now we're going to switch over to a very specific pigment, but probably the most used pigment, which is titanium dioxide. I think on the first slide here I just show a commercial data sheet I just found on the web from what happens to just be a large chemical company. And this is showing off they manufacture the two different crystalline forms of titanium dioxide. This is the crystalline structure of anatase, TiO2, and this is the crystalline structure of rutile. And what they're showing here is two different grades of this titanium dioxide showing particle size as measured on the instrument it seems they're using to do these measurements. That's not a endorsement from this company. This is just pulled off. They put that name right on all of the batches of all of the products that they ship for TiO2, because I believe they use quite a few HORIBA laser diffraction analyzers to keep track of the particle size of their titanium dioxide. They note down here that the lower median particle size and the narrow distribution as defined by the geometric standard deviation makes this higher scattering efficiency essentially a better pigment for paint. It's interesting to note they actually talk about the geometric standard deviation. So there are various ways you could define the breadth of this distribution. One of the calculations, which is standard in the LA 950 software, is GSD, geometric standard deviation. And I've met several people, perhaps from this company, who say that, you know what, that's a really good indicator of the quality of the pigment going into a paint. And this will be a solid indicator of how well will this disperse as a function of time. So they really watch the GSD as they generate the titanium dioxide, and that generates a higher quality paint. So when we see some results later on for titanium dioxide, you'll probably see us reporting this value, the GSD, geometric standard deviation. Just a few images of why particle size is so important. This is talking about relative scattering efficiency, scattering power. So in the previous slide, it mentioned this about the scattering efficiency as a function of size. So this is relative scattering power. This is particle size going up. This is 100 nanometers. That's 200 nanometers. And this is saying this is actually also a function of the wavelength of light where you measure this with for red, green, and blue. But what you would see is for several wavelengths, there's this maximum right at around 220 nanometers. And that's one of the magic numbers for titanium dioxide. If you can get TiO2 dispersed so that the median particle size is 250 nanometers or a little under, that's just kind of a sweet spot where you maximize the scattering power and therefore is probably the better pigment to use. If you want to just look at paint samples to see the effective particle size, these are samples of TiO2 paints sprayed onto a surface. Here on the left we see the much whiter color. The median particle size was 0.25 microns, which is 250 nanometers. But if the particle size gets larger, you'll see it doesn't really look so white, does it? So the scattering power is not as high. And so this is just a visual way to understand, does particle size really matter? Oh, it certainly does. And for TiO2, this is where you'll see a lot of specifications for the pigment used for various applications, including paint. So if we talk about procedurally how one would go about measuring titanium dioxide, I already gave this away. The first thing you should do, of course, is buy a HORIBA LA950. That is the instrument of choice for most large manufacturers of TiO2 with good reason. Ease of use, dynamic range, ability to measure down into this nanometer scale. You can decide, even with TiO2, even with small size distributions of TiO2, as you'll see in a few slides, you can still measure it either as a dry powder or disperse it in liquid. If we're going to disperse it in liquid, then we probably are going to do some method development looking at the proper surfactant and the right concentration of surfactant. Should we use ultrasound? I think somewhere on my computer I have a published method for dispersing TiO2, and I think it uses PhotoFlow as the surfactant. Sometimes, often it's dispersed in sodium hexametaphosphate, not just in DI water. And it is typically dispersed using ultrasound, either an external probe or just the probe built into the LA950. So once we get the chemical nature of the method development organized, then we actually are going to, if it's a new product, do some method development with our hands on the instrument. And when we're doing this, if we're using the LA950, we could be using our Method Expert software features where we can automatically look at the effect of anything that might affect the result, such as the choice of refractive index. The concentration we measure at turns out to be fairly important for pigments. Pigments are one of the samples that are fairly sensitive to concentration. And it makes a lot of sense to measure these kind of samples at different percent transmissions, different concentrations, and look at the effect so that you design your method around an area that is most robust and reproducible. How much ultrasound should we use? This could also be automated using the Method Expert software. I'll show, I think, one slide from Method Expert in this talk, but if you want to hear more about this, again, that would be one of the other recorded webinars on method development. And if we're going to just measure it as a dry powder, typically we'll just use the smallest nozzle, so we have the highest efficiency for dispersion, and probably run up at the maximum air pressure, something up near 4 bar. But as I get started with a new sample like TiO2, one of the first things I might do is say, well, what should I use for refractive index? We should find a way to determine the real component of refractive index. We will fix that, but then what should I use for the imaginary value? If you're not familiar with these terms, real refractive index, imaginary, I think it was just a month ago we recorded a webinar on the effect of refractive index and how this selection of refractive index is automated using the Method Expert software in the LA950 software. What we do is we measure it once, fix the real value. Here we fix the real value, as you see, at 2.75. And then we varied the imaginary component. Here you see we varied it from 0 to 0.01, 0.1, 1, and 10. What the software will then do is it'll take the one file that has already been created during that initial measurement, And then it calculates the size distribution with these different values of refractive index. It shows you the calculated results here. Down below here you see D10, D50, D90 versus the R parameter. The R parameter is the value that tells us something about the error calculation. So this is D10, D50, D90, sorry, as a function of refractive index. And this last graph is showing refractive index, the real is fixed, we're varying the imaginary from 0 up to 10. And this R parameter is an error calculation. And what you see is the error calculation minimizes when we choose an imaginary value of 1. Therefore, this is the imaginary value we will use for this pigment on the LA950. For this sample, and henceforward, we will use the refractive index of 2.75 for the real component and 1 for the imaginary. And this is all automated with the Method Expert software. And it really is an important decision that needs to be made, and it's a great way to automate that decision. So we've decided what we're going to do for refractive index. This is TiO2 that we measured for a cosmetic study. And we see maybe there's still some aggregates. We certainly did do some method development, and we used ultrasound for this. You'll see there are particles below 0.1 micron, 100 nanometers. And in the cosmetics industry, there's an interest in this percent under 100 nanometers because we could define these then as nanoparticles. Nanoparticles, something under 100 nanometers. And right in the LA950 software, we can present the percent under any diameter. In this case, the percent under 100 nanometers, and we see there's about 14.5% of the total under 100 nanometers. And this may be of interest to people. The particle size is important. Maybe they're trying to avoid nanoparticles. Maybe it's not important. I don't know. But the instrument's quite capable of measuring down in the size range and conveniently reporting it right here so that you know immediately what's the percent under the size, 100 nanometers, or any other size you choose. You could tell what's percent over 1 micron. Remember on an earlier slide we saw that was important. We could add that as another value, automatically reported each time we do this measurement. We had some customers send in some TiO2 to the laboratory there in Irvine. And when we do method development, another way to make sure you're getting a good dispersion is it came in as a powder. You can measure it as a powder, as we see here with the red or red-orange distribution. And then we dispersed it and measured it as a liquid. And it just gives you that added confidence in your results. If you get similar results, measuring it both dry and dispersed in a liquid, in this case it was in DI water. And let's just look at some of the values here. So if you look at the D50, the median for the dry dispersion, that's 0.346, and wet is 0.355. So those are pretty similar numbers. So that's pretty impressive. If you look at the median, there's only an 8 nanometer difference between these two. That's one impressive result we're looking at from this work, which was done by Kiwan there in our lab in Irvine. He was on his game this day. The other interesting thing we note here is a dry powder being able to disperse down at 350 nanometers. I'm not sure every instrument in the world can do that. In a tail down under 100 nanometers as a dry powder, I think we're seeing one of the reasons why people who make TiO2 use HORIBA instruments, because it generates data like this. We then were challenged by the customer to say we have slight differences between these two samples. Can you pick up on it? So we have sample number 1 and we have sample number 2. We see this sample had a median of 0.334 and this 0.346. And it's a 12 nanometer difference, but it was very reproducible. So that's showing the ability to resolve these very small differences between particle size distributions using the LA950. So that is quite an instrument that can actually pick up differences in grades of finely dispersed TiO2 where there's only a 12 nanometer difference. So excellent data, excellent instrument. I think some of the last data we'll look at here is what happens when the particles are even smaller than down here on the 100 nanometer scale. This is actually data that was just published, that I found published in an article. This is from a HORIBA LB500 several generations ago, but one of the HORIBA dynamic light scattering instruments. I'm not sure exactly how you define nano TiO2. We'll just say it's small titanium dioxide. What you see here, the median size, here would probably really be talking about maybe Z average, but it's down under 10 nanometers. So if your samples are all down to 10 nanometers and lower, then you're not going to be using laser diffraction, ours or anyone else's. You're probably going to be using dynamic light scattering. So for the smallest size distributions you see in the world of pigments, that's when we switched to dynamic light scattering. This was from an older model. But using our newer model, we can actually measure down here in the range of down to a nanometer. This particular sample, which I just ran a few weeks ago here in France, where I live, this was actually larger. This was up at 566 nanometers, but a very tight distribution. I was impressed by that. So here, if everything's under a micron, maybe we switch to using dynamic light scattering. And we have other presentations if you want to hear about HORIBA in dynamic light scattering and the SZ100, which is our newer instrument for dynamic light scattering, that measures both particle size. And down here you see zeta potential for titanium dioxide. The pH is very important when we measure zeta potential. It's really a function of the surface chemistry of the sample as we measured it. So certainly for pigments, we always report the pH where the sample was taken. At pH 7, this titanium dioxide had a zeta potential of -48, pretty much where we would expect it to be. So this was just some samples came into the lab. We ran these here in France and did particle size very easily, measured the zeta potential. I will just point out, if you send us samples for titanium dioxide and you want to know the zeta potential, please send it to us dispersed as you typically disperse it, because, as I'd mentioned before, the zeta potential is this function of the overall surface chemistry. And if you disperse it with a certain surfactant and we disperse it a different way, we'll get a different answer, which may not be as meaningful to you if your goal is to find the best conditions for dispersing the sample. But if we do that, then we're happy to also show you what can be generated with our new DLS instrument, the SZ100, measuring particle size down here in the sub-micron range, even down to sub-nanometer for the most difficult samples. And we can also measure particle size. So far you've just heard kind of easy measurements. In general, the data we generated here weren't all that hard to generate. Particle size is critical for this realm of pigments. I will say I should be careful. You know, when you do the method development of pigments, the choice of refractive index is very important. The concentration is important. The dispersion is important. So I shouldn't say they're the easiest samples out there. They really aren't. What I should say is if you understand method development, and we're very happy to help you get there, and you're using the right tool, such as the LA950, then you really would have both the instrument and the capability, as I make out here, and certainly with the support of the applications team, to generate the kind of data you saw here today, a very reproducible data for pigments of various size ranges, very small up to larger, and with the new SZ100, even down into that range of, you think now you're down in the 10 nanometer range. 10 nanometers is not any challenge to the SZ100 and smaller. And now we can do that work both for particle size and help you perhaps with the dispersion. Maybe you want to do an isoelectric point test of how does zeta potential change as a function of pH. We have a webinar on doing those kinds of tests as well. And that could be used, for instance, for a formulator, looking at the best ways to create formulation of new pigments used in paints or in other applications. So you've seen the data that can be generated here. And Ian, myself, Kiwan, Amy, the whole rest of the team are around to help walk you through these method development and dispersion challenges. We actually enjoy doing that. So if we do end up being your supplier for particle size, that's something we're very happy to help you with.